Bismillahirrahmanirrahim. So here we have this problem. Assume that there is no initial energy stored in the circuit of figure 1 at time t is equal to 0, and that Is is equal to 10 u of t. This is Is here, 10 u of 2 amperes. And part A, find V naught S using Thevenin's theorem. V naught S is the Laplace transform of this time domain voltage V naught T across this resistor, right? And part B, apply the initial and final value theorems to find V naught at time t 0 positive and V naught at time t infinity. And part C, determine V naught T. So let's begin the solution. With part A, so which is V naught S using Thevenin's theorem. And before we do that, we need to transform this circuit in the frequency domain. So the significant thing here is IFS at which is 10 u of t. So the Laplace transform for this will be, so 10 u of t when transformed to the S domain is 10 over S, and this Ix will become Ix of S. We represent this with capital letter. This 5 ohm resistor remains the same as the S domain. This is not affected, but this 2 Henry inductor becomes SL, which is S multiplied by L, which is 2 Henry. So this is 2S. So we can redraw this circuit in the frequency domain like this. Let's call this fig 2. This is 5 ohm and this is 2S now. This current is Ix and this is then 2Ix. This is 10 over S and this is 5 ohm and this is V naught S now, right? So V naught T becomes V naught S in the frequency domain. So first we find there are two parts to solving Thevenin equivalent circuit. We need to find the Thevenin's open circuit voltage, and we need to find out the Thevenin impedance, right? So to find the Thevenin's open circuit voltage, we take out this resistor R here, this 5 ohm resistor here, and find the open circuit voltage across these terminals. So to find Thevenin voltage, we represented V Thevenin, open circuit Thevenin's voltage, V Thevenin. We remove 5 ohm resistor, right? So then we have this circuit here. So this is 2S, right? 2S, and this is I of X, right? and this is 2i of x. This is because, let's call this 2ix1 now, because we have opened the terminals. So this is ix1, this is 2ix1, this is 5 ohm, and this is 10 over s. Let's call this fig 3. So this voltage here, open circuit voltage, is Thevenin, open circuit voltage, right? So and note that the potential drop across this inductor is 0, because there is no current flowing through it. There is no way that the current flow through it. So the current flowing here is 0. So Ix is 0, right? So we can see that Ix1 is equal to 0. So therefore this controlled source 2Ix1 is also equal to 0. So all this current 10 over s flows through this 5 ohm resistor, and there is no way, there is no current through this this inductor. So we can say that all the voltage drop is across this resistor, 5 ohm resistor, and the voltage drop this resistor is the open circuit voltage, open circuit OC, open circuit voltage, which is the Thevenin voltage. So V Thevenin is equal to V open circuit, and is equal to 5 multiplied by 10 over s. This 5 ohm resistor multiplied by this current flowing through it, because let me say it again, this Ix1 is 0. There is no current flowing here. So Ix1 is 0. And 2Ix1, this is 0. Right? So this is short circuit. So the voltage, all the voltage drops across this resistor, and this appears as the the volt at the output terminals, because if we apply KVL here, so this will give us the voltage here. So this will be V Thevenin is equal to 50 over s. This is the open circuit voltage, right? And the second part of finding the Thevenin equivalent circuit is determining the Thevenin impedance. So as we have a controlled source in the circuit, what we need to do is either find the short circuit current here, then the Thevenin impedance will be equal to open circuit voltage divided by the short circuit current, or we can apply a known voltage or current source here and then apply the other parameter. If we apply a known voltage source here, then we find out the current, and then the known voltage source divided by the current will give us the Thevenin impedance. Or if we apply the known current source here, for example 1 over current source here, then we find the voltage across it, then the voltage divided by the current will give us the Thevenin impedance. So we can adopt any of these methods. So in any case, we need to redraw this circuit. So let me redraw it again. So this is 10 over s, this is the control source, 2Ix, this is 5 ohm, this is 2s impedance for the inductor, right? And we have these terminals. So if we add a source here, voltage or current source, we have this node, and we have to apply nodal analysis or the mesh analysis to solve this. Or if we short circuit this, again we have same two loops or this node analysis to solve for this circuit. So if we add a source here, this will be an additional element to deal with. So it's better that we short this off and find the short circuit current. So this current is Ix, and this current is the same as this one, but we call this short circuit current, right? So Ix is equal to this short circuit current, and let's call this Ix2 because this current is not the same that will flow here, this Ix here, because this Ix flows when this is 5 ohm resistor connected across these terminals. So let's call this Ix2. So Ix2 is equal to ISC, short circuit current. So let me call this fig 4. So here in this figure, the short circuit current ISC is equal to Ix2, right? And we can we can find out the nodal voltage here, node voltage here. This is the reference node. Let's call this V1, right? And V1 divided by 2S will be Ix2 or ISC, whatever we call it. So let's apply this, write the equation for this node. So that will be minus at node V1. So this is current flowing into the node. We assume that all the currents are flowing away positive and flowing into negative. So that will be minus 10 over S plus V1 minus 2Ix2, V1 minus 2Ix2 divided by 5 and plus V1 divided by 2S, and that is equal to 0. So multiply throughout by 10S, right? So this will become minus 100. 10S multiplied by minus 10 over S will be minus 100, and this will be 2S into V1 minus 2Ix2, right? V1 minus 2Ix2 multiplied by 10S divided by 5, that is 2S, and plus this will be 10S divided by 2S, that is 5V1 is equal to 0. So this will be minus 100 plus 2S V1 plus 4S Ix2 plus 5V1 is equal to 0. But Ix2 is equal to ISC, short circuit current, and that is equal to V1 over 2S. This V1 is the voltage across this branch, and this V1 is the voltage across this entire branch. And V1 and the impedance of this entire branch is only 2S. So V1 divided by 2S gives the current through this branch, which is Ix2 or ISC. So we put this value here. So this will be minus 100 plus 2S V1 plus 4S into V1 divided by 2S plus 5V1 is equal to 0. So this cancels with this and leaves us with 2 here. So this is minus 100 plus 2S V1 plus 2V1 plus 5V1 is equal to 0, right? So this will be 2S plus 7, 2S plus 7, right? So let us have a look at this entire process again. Minus 100 plus 2S into V1 minus 2Ix2 plus 5V1 is equal to 0. So minus 100 plus 2S V1, and this should be minus here, right? Minus 4S Ix2 plus 5V1 is equal to 0. But this Ix2 is equal to ISC is equal to V1 over 2S, right? This is correct. And minus 100 plus 2S V1, and this should be minus here. and minus 2v1, and this leaves us with this 5v1 here, minus 100 plus 2sv1 minus 2v1 plus 5v1. So that is basically 2s and 2sv1 plus 3v1, right? So 2s and 5 minus 2, this is 3v1, and that is equal to 100. So v1 is equal to 100 divided by 2s plus 3. So this is the voltage across this node, and we still need to find the voltage across the across this resistor, and for that we are finding the Thevenin equivalent circuit. We have found out the Thevenin voltage, which is 50 over S, right? And we are now determining the short circuit current. So we have found V1, so the short circuit current ISC, which is equal to IX2, is equal to V1 divided by 2S. So this is equal to V1 divided by 2S. So the short circuit current is equal to V1 is this 100 divided by 2S into 2S plus 3. So the short circuit current is equal to 50 divided by S into 2S plus 3. So this is the short circuit current. So the Thevenin impedance is given by, let's call this Z Thevenin, ZT is equal to open circuit voltage divided by the short circuit current. And we found that the open circuit voltage was which is V Thevenin, which is 50 over S divided by the short circuit current, which is 50 divided by S into 2S plus 3. So Z Thevenin is equal to 50 over S multiplied by S into 2S plus 3 divided by 50. So this 50 cancels with this S cancels with this, so leaving us with this S cancels with this, right? So leaving us Z Thevenin is equal to 2S plus 3. So Z Thevenin is equal to 2S plus 3. So we have found out the open circuit voltage, Thevenin open circuit voltage 50 over S, and we have found out the Thevenin impedance, that is 2S plus 3. So we can draw the Thevenin equivalent circuit. The Thevenin's equivalent circuit is as below. So this is Thevenin voltage, this is the Thevenin impedance, and these are the open terminals. So this is V Thevenin is equal to 50 over S, and this is Z Thevenin, which is equal to 2S plus 3, right? So let me call this, this was figure 4, let me call this fig 5. So to find the current through 5 ohm resistor, we connect this resistor across these terminals. Ohm, and this is 2S plus 3, this is 50 over S, and this is 5 ohm. And rather we want to find the voltage, right, not the current. We need to find V naught S using Thevenin's theorem, and V naught T is this, and we need to find out V naught S, right? So this is V naught here. So V naught of S is equal to, we can now apply the voltage divider rule. So this is 5 divided by 5 plus this impedance 2S plus 3 and multiplied by this voltage, which is 50 over S. So V naught S is equal to, this should be 250, right, divided by S into, so this is 2S and plus 8, right. So V naught S is equal to 250 divided by, we take the 2 common here, so that is 2S into S plus 4. Yeah, so this can be rewritten, is this 2 will cancel and leave us with 125 here. So V naught S is equal to 125 over S into S plus 4. So V naught S is this. So we have completed our part A, which was to find V naught S using Thevenin's theorem, right? And we have found out V naught S is equal to 125 over S into S plus 4. So now to the second part, part B. Apply the initial and final value theorems to find V naught at time t0 positive and V naught at time t infinity. So let's proceed to our part B. Part B. And for that, let's rewrite V naught S, and that was found out to be this here, 125 over S into S plus 4. And now the initial and final value theorems. According to initial value theorem, the value of the inverse Laplace transform V naught t at time t0 is given by V0 at time t0 is given by this limit here, limit S tends to infinity and S multiplied by V naught S, right. So so let's multiply this S with V naught S. So this will leave us with limit S tends to infinity. So S multiplied by which this S will cancel this S here. So that will leave us 124 over S plus 4. So to apply this limit to the infinity, we need to divide the numerator and the denominator by S. So limit S tends to infinity. So we have 125 over S, and this is 1 plus 4 over S. And when this now tends to infinity, this term is 0, the numerator is 0, and divided by 1 plus this term is also 0. So that leaves us 0. So V0 at time t0 is 0, right? And according to the final value theorem now, according to final value theorem, V naught at time to infinity is limit when S tends to 0, S V naught of S, if all poles are in the left half of the plane, if poles are in left half of the plane, or if there is a simple 0 at origin. So in this case, or if there is a simple zero at the origin, this is true for V naught S. All the poles, we have a one pole, S is equal to -4. This is in the left of the plane, and we have a simple pole at the pole, sorry, not zero, simple pole at the, we have simple pole at the origin. So this condition is satisfied for this Laplace transform of V naught t. So we can apply the this final value theorem. So V naught t, V naught at time t infinity is equal to limit s tends to 0. So s multiplied by V naught s will leave us with 125 over s plus 4. So V naught at infinity, we put s here, so this leaves us with 125 over 4. So 125 over 4, 125 divided by 4 is equal to 31.25, is equal to 31.25, right? So this is the final value at time t infinity of V naught t, and this is the value of V naught t at time t 0. Let us now find V naught t, which is our part C, right? So the part C is determine V naught t. Part C is what is V naught t. We need to determine the value of V naught t. So for this we need to find the inverse Laplace transform. For this we need to expand this using the partial fractions. So let V naught is equal to 125 over s into s plus 4 is equal to a over s plus b over s plus 4. So if we multiply it throughout, multiply by s, so this will give us s V naught is equal to 125 over s plus 4 is equal to a plus bs over s plus 4. So now if we let s is equal to 0, then this term will disappear because this is multiplied with s is equal to 0, and this will leave us with only b. So a is equal to s V naught when s is equal to 0 is equal to 125 divided by s plus 4, s is 0, so that is 4. So 125 over 4 is 31.25. So a is equal to 31.25, right? Likewise, let's call this 1. So multiply 1 by now s plus 4. So this is s plus 4 V naught is equal to 125 over s, right? S plus 4 is eliminated because we're multiplying with it. So that is a over s into s plus 4 plus b, right? So let s plus 4 is equal to 0 now, that is s is equal to -4. So this will eliminate this term and this will leave us with b only. So b is equal to s plus 4 multiplied by V naught when s is equal to -4 is equal to 125 divided by the value of s is -4. So 125 by 4 again, and there is minus 31.25. So b is equal to minus 31.25, right? So we can write this V naught here. V naught of s is equal to a is this a is 31.25 divided by s, right? And this b term minus 31.25 divided by s plus 4. And if we take the inverse Laplace transform, this is 1 over s. So the 1 over s or 31.25 over s, it's the Laplace transform of u of t, and 1 over s plus 4 is the Laplace transform of e raised power minus 4t. So we can write v naught t is equal to 31.25 u of t minus 31.25 e raised power minus 4t u of t. So we can take this 31.25 common. So v naught t is equal to 31.25, this is 1 minus e raised power minus 4t and u of t. Note that u of t here signifies that this value exists for time t greater than or equal to 0. This function is valid for time t greater than or equal to 0, right? Because we consider the Laplace transform. When we derive the Laplace transform, we take the limit from 0 to infinity. So this is single-sided Laplace transform. So 31.25, 1 minus e raised power minus 4t u of t. And we can now verify that at time t0, this becomes e raised power 0, and e raised power 0 is 1. So 1 minus 1 is 0. So v naught 0 at time t0 is 0, which we found earlier here. And if we put t is equal to infinity here, so this will be 1 over e raised power 4t, and t is infinity. So 1 over e raised power infinity. So 1 over e raised power infinity is 0 basically, right? So this will be 1 minus 0. So that will leave us 31.25 multiplied by 1, that is 31.25. So the value of this function at time t infinity will be equal to 31.25, which we found out earlier here, right? So this verifies our earlier results also, and this gives us the voltage v naught t, the voltage across the 5 ohm resistor here, right? This voltage v naught t, and we found out using Thevenin's theorem. We could have found out by other means, but we were asked to find out using Thevenin's theorem. So we first derived the Thevenin's theorem by removing this resistor across these terminals, and once we found out the Thevenin equivalent circuit here, then we connected this resistor, 5 ohm resistor here, and then found out v naught s using the voltage divider rule. And once we found out v naught s, we applied initial and final value theorems to determine the values at time t0 and at time t infinity. And finally, by taking the inverse Laplace transform, we found out v naught t, the expression for v naught t, which is the voltage across the resistor.